6.5 Integrating hyperbolic functions. Now you can integrate hyperbolic functions and you should be familiar with these results shown here. The integral of hyperbolic sine x, that's equal to hyperbolic cos x plus c, and that's because differentiating hyperbolic cos we get sine. Integrating hyperbolic cos x we get hyperbolic sine x, and that's because if we differentiate hyperbolic sine x we get hyperbolic cos x. If we integrate 1 over the square root of 1 plus x squared with respect to x, we get the inverse of hyperbolic sine x, and that's because differentiating inverse hyperbolic sine x is equal to 1 over 1 plus x squared square rooted. And if we have the integral of 1 over square root of x squared minus 1 with respect to x, then that turns out to be inverse hyperbolic cosine x plus c, where x is greater than 1, and that's because differentiating inverse hyperbolic cos x we get 1 over square root of x squared minus 1, where x is greater than 1. Now, of course, in the formula book, if you take a look at the standard derivatives, and we see those here, you can essentially work out to go from f dash to f, we need to integrate. So essentially, we don't have to memorize a lot. And I'd also like to pay your attention to integrating hyperbolic sec x squared, we get hyperbolic tan x, and integrating 1 over 1 minus x squared, we get inverse hyperbolic tan x. Example number 23, we have to find the integral of hyperbolic cosine of 4x minus 1 with respect to x. So to do this we need to use the result over here. Now of course we'd have to use the reverse chain rule to help us do this. We divide by the differential of the bracket. So if we work this out, we end up with 1/4 times by hyperbolic sine of 4x minus 1 plus c. Example number 24, we have to find the integral of 2 plus 5x over square root of x squared plus 1 with respect to x. So to do this we need to split this numerator up so that we have something which is more integrable. So we can split this up as the integral of 2 over square root of x squared plus 1 with respect to x plus integral of 5x over square root of x squared plus 1 dx. Now to do this, here we can use the reverse chain rule, here we can use the standard results which we saw over here. So if we take out the 2, we have 2 lots of the integral of 1 over square root of x squared plus 1 with respect to x. And then here, well, what we can do over here is rewrite this as the integral of 5x lots of x squared plus 1 to the power of minus 1/2 with respect to x. So if we deal with what we have over here, hopefully here you can see the integral of 1 over square root of x squared plus 1, that's the inverse hyperbolic sine of x. So here we have, if we work this out, we've got two lots of inverse of hyperbolic sine of x. And if we deal with this result, well, to do this, what we can do is recognize that the differential of the bracket is almost on the outside of the bracket. What I want this to say is 2x lots of x squared plus 1 to the minus 1/2 dx. But I don't have a 2, I've got a 5, so I need to multiply by 5/2. So we've got 5/2 lots of the integral of this result over here. So now here we can use the reverse chain rule. We've got the 5/2, and then if we use the reverse chain rule, we've got 2x lots of x squared plus 1 to the power of 1/2, so we add 1 to the power, and then we divide by the new power. The new power is 1/2, and then we divide by the differential of the bracket, which is 2x. So this is what we have. We've got two lots of the inverse of hyperbolic sine x plus this result over here. And if we tidy all this up, hopefully here you can see we've got two lots of inverse hyperbolic sine x plus 5 lots of x squared plus 1 to the power of 1/2 plus c. And if you want, you can rewrite this as 2 times by the inverse hyperbolic sine of x plus 5 lots of x squared plus 1 square rooted plus c. Example number 25. For part A, we've got the integral of hyperbolic cosine of 2x to the power of 5, and I'm going to rewrite this result like this, multiplied by hyperbolic sine of 2x with respect to x. Now, to do this, of course, you'll recognize that the derivative of what's in this bracket is outside of the bracket, so we can use the reverse chain rule. So to do this, we add 1 to the power, so we have hyperbolic cosine of 2x to the power of 6. We then divide by the, and don't forget we still have the hyperbolic sine of 2x. We then divide by the new power, and then we divide by the differential of the bracket. So the differential of the bracket is 2 hyperbolic sine of 2x, and don't forget we've got the plus c, so hopefully here you can see 6 times by 2, that's 12, so we've got 1/12 lots of hyperbolic cosine of 2x to the power of 6 plus c. Now for part B of the question, we have to integrate the hyperbolic tan of x with respect to x. And what you'd hopefully recognize over here, hyperbolic tan, that's the same as hyperbolic sine over hyperbolic cosine. And here, this is of the form f dash over f. The derivative of the bottom is on the top, and because of that, we can conclude that this is the natural log of the hyperbolic cosine of x plus c. And you'll notice we're not including a modulus sign here because hyperbolic cosine x is always greater than 0 for all values of x. Now, what we can say then in conclusion following that example is that the integral of hyperbolic tan x, that's equal to the natural log of hyperbolic cosine x plus c. Now for example number 26, we have to find the integral of hyperbolic cosine of 3x all squared. So to do this, for part A, we've got the integral of hyperbolic cosine of 3x all squared, and we need to use the identity hyperbolic cosine of 2a is equivalent through Osborne's rule of 2 times by hyperbolic cosine a squared minus 1. And you can see here a is equal to 3x. So what we have over here then is the integral of, if we rearrange this result, we've got the integral of 1 plus hyperbolic cosine of 6x all over 2 dx. So if we work this out, well, we've got 1/2 being integrated, which is a half x, and then we've got a half cosh 6x being integrated. Well, of course we'd have to divide by the differential of the bracket. The differential of the bracket is 6, so we have to divide by 6 as well. So we end up with 1/12, because we've got a 6th times by a half, times by hyperbolic sine of 6x plus c. Now for part B of the question, slightly more tricky. We've got the integral of hyperbolic sine x cubed dx. Now to do this, we can use the result over here that, if we write it down, for odd values of n, the integral of hyperbolic sine x to the power of n dx, that's equal to the integral of hyperbolic sine of x to the power of n minus 1 times by hyperbolic sine of x. And that's because when we add the powers we get this result over here. So, and you'll see why I'm doing that in a second. What we can say over here is we've got the integral of hyperbolic sine squared times by hyperbolic sine. So now when we come to integrate this result, hyperbolic sine squared, that's the same as hyperbolic cosine squared minus 1. So we've got this integral being multiplied by hyperbolic sine x dx. So if we expand the brackets, we've got the integral of hyperbolic cosine squared times by hyperbolic sine x minus hyperbolic sine x dx. So if we integrate all this, here the differential of cosine is sine, so here we can use the reverse chain rule, and perhaps if I rewrite this result as hyperbolic cos all squared times by sine x, and don't forget we've got the dx, and then we've got minus the integral of hyperbolic sine x dx. Now here we can add 1 to the power, so we have hyperbolic cosine x to the power of 3, and we still have this hyperbolic sine x. We then divide by the new power, which is 3, and then divide by the differential of the bracket, over here, which is hyperbolic sine x. And here, if we integrate hyperbolic sine, we get hyperbolic cosine. And don't forget we've got the plus c. So if we tidy all of this up, hopefully here you can see we've got 1/3 times by hyperbolic cosine x cubed minus hyperbolic cosine of x plus c. So that's why we rewrote this result. So our answer is in a more integrable form. Sometimes the exponential definition of a hyperbolic function can be used to find a given integral. So let's take a look at an example to help illustrate this. Let's suppose over here, for example number 27, we wish to find the integral of e to the 2x times by hyperbolic sine x with respect to x. Now the way we approach this is to use the definition of hyperbolic sine. So this is the same as e to the 2x multiplied by e to the x minus e to the minus x all over 2 dx. So now what we can do is, if we take out the half as a constant, and then if we use the laws of indices, we've got e to the 2x times by e to the x, that's e to the 3x. And then e to the 2x times by minus e to the minus x, that's minus e to the x. And we're integrating all of this with respect to x. So we've got 1/2 times by 1/3 e to the 3x, and then we subtract off 1/2 times by e to the x, and don't forget we've got the plus c. So if we tidy all this up even further, you can see here we've got 1/6 e to the 3x minus 1/2 e to the x plus c, and if you want you can take out the 1/6 as a common factor. We've got 1/6 times by e to the 3x. Now here, minus 3 times by a sixth gives the minus 1/2, so we've got minus 3 e to the x as well. And don't forget to add your plus c. You need to be able to use hyperbolic substitutions to find the integrals of expressions of the form 1 over square root of x squared minus a squared and 1 over square root of x squared plus a squared. Now, if you take a look in the formula book, we've got these various different integrals which we need to work out. Now, in the exam, instead of us having an x, we'd have something more complicated than an x. And therefore, in that case, we'd have to use substitutions. So, in this part of the video, I want to talk about which substitution to use and when. And this will be a very good summary of general integration problems. Now before we do anything, I think it will be a good idea to think about some Pythagorean identities. And if you pay attention to why we're talking about Pythagorean identities, is because you can see in each of these 6 cases we have something which looks like it could involve Pythagoras. So if we think about some Pythagorean identities, let's just write them down. Writing down the Pythagorean identities for regular trig, we begin with sine squared x plus cos squared x being equivalent to 1. And I'm going to rearrange this, and you'll see why later on. I'm going to rearrange this to say that sine squared x is equivalent to 1 minus cos squared x. And I'm also going to rearrange to say that cos squared x is equivalent to 1 minus sine squared x. You'll see why I'm doing this in a second. And we've also got other identities as well. We've got 1 plus tan squared x being equivalent to sec squared x, and therefore we can see that tan squared x will be equivalent to sec squared x minus 1, and we've also got 1 plus cot squared x being equivalent to cos x squared x, and we can also rearrange this to say that cot squared x is equivalent to cos x squared x minus 1. Now, if we think about the corresponding hyperbolic identities, well, we'd have to use Osborne's rule. And remember, for Osborne's rule, wherever we've got a sine squared, we replace that with minus hyperbolic sine squared. So if we can think about this Pythagorean trig identity, the corresponding hyperbolic identity will be minus hyperbolic sine squared plus hyperbolic cos squared being equivalent to 1. And if we rearrange for this, hopefully here you can see hyperbolic cos squared is equivalent to 1 plus hyperbolic sine squared. And if we rearrange for hyperbolic sine squared, hopefully here you can see this is equivalent to hyperbolic cosine squared minus 1. And if we think about the corresponding hyperbolic identity for 1 plus tan squared equivalent to sec squared, again using Osborne's rule for the tan squared, when we come to find out the corresponding hyperbolic for tan squared, that will be minus hyperbolic tan squared because of Osborne's rule. So we have 1 minus hyperbolic tan squared being equivalent to hyperbolic sec squared. And if we rearrange from here, hopefully here you can see hyperbolic tan squared, that's equivalent to, if we rearrange, 1 minus hyperbolic sec squared. And if we think about this identity over here, the 1 plus cot squared being equivalent to cos x squared, again using Osborne's rule, where we've got the cot squared, the corresponding hyperbolic will be minus hyperbolic cot squared. So we've got 1 minus hyperbolic cot squared being equivalent to minus hyperbolic cos x squared x. And if we rearrange our results, hopefully here you can see we end up with hyperbolic cos x squared being equivalent to hyperbolic cot squared minus 1, and we've also got hyperbolic cot squared being equivalent to hyperbolic cos x squared plus 1. Now, why is this result important? Because this will allow us to help us identify which substitution to use when we don't have an x. Instead of us having an x, we'd have something a bit more complicated, say f of x. So the idea over here is going to be, if we've got something involving an a squared minus an x squared square rooted, or an a squared plus x squared, or an x squared minus a squared square rooted, or an a squared plus x squared square rooted, or an a squared minus an x squared or an x squared minus an a squared, the idea is over here we're going to be using a substitution. So let's see how we go about this. And of course, whenever we use substitutions, you'll notice here we've got terms which are squared, and therefore we'd have to use our Pythagorean identities. The idea is over here we're going to be matching up as necessary with whatever we have over here. Now, just as some sort of a warning, whenever you've got square roots, so that's here, here, or here, you're going to be dealing with sines, cosines, hyperbolic sines, and hyperbolic cosines only. And whenever you don't have the square root, that's when you have the tan, the cot, hyperbolic tan, and the hyperbolic cot. So let's take a look at a couple of different scenarios with all these. Now, one situation which we could have is having something like, in our integral, a squared minus f of x squared square rooted. Now, in this situation, we need to think about some of the Pythagorean identities. So, if you look at what we have over here, essentially you can think of the a to be 1 and the f of x being something involving trig or hyperbolic trig. So if we have something of the form a squared minus f of x squared, hopefully here you can see that matches quite well with this one over here and this one over here. And remember, because we're square rooting, we only consider the sine or cosine. We could consider hyperbolics as well, but there's nothing that we have for a hyperbolic which contains sines and cosines only. So we can't use this one, and we can't use this one. So the only two options we have are using this one or using this one over here. So if we have this one over here, we have 1 minus cos squared x being equivalent to sine squared x. So in this situation, what we do is we let our substitution be cos of u, okay, because we've got a cos over here, equaling f of x over a. So that's one way we can approach this. The other way we can approach this is by using this identity here, which is 1 minus sine squared x being equivalent to cos squared x. So if we think about the substitution we're going to have sine of u equaling f of x over a. Another situation which we could have is if we've got something of the form f of x squared minus a squared. Now in this case, you can see we don't have something which is square rooted. So if we go to our Pythagorean identities, we don't want anything containing sine or cosines or hyperbolic sines or hyperbolic cosines. So one option which we could have is the option over here. You can see these match up quite nicely. And another option which we could have is this one over here. So we've got sec squared x minus 1 being equivalent to tan squared x. And in terms of the substitution we will make, well, here we'll have sec of u equaling f of x over a. Another one which we could have is this one here, cosec squared x minus 1 being equivalent to cot squared x. So if we match everything up, hopefully here you can see for our substitution we're going to have cosec of u equaling f of x over a. Now if we've got something of the form a squared minus f of x squared, again let's take a look at our Pythagorean identities. We're not square rooting, so we're not going to think about anything involving sine, cosines and the hyperbolic sine and cosines. So if we think about what we can have if we try to match everything up as necessary, hopefully you can see we've got this result over here, 1 minus hyperbolic tan squared equals hyperbolic sec squared. And that's the only one which matches up with what we have over here. So we'll be using the identity 1 minus hyperbolic tan squared being equivalent to hyperbolic sec squared. So if we think about the substitution which we need to make, we've got hyperbolic tan of u equaling f of x over a. Now let's suppose we've got something in our integral of the form a squared plus f of x squared square rooted. Now because we're square rooting, we're going to have something involving sines or cosines or hyperbolic sines or hyperbolic cosines. So if we take a look at our Pythagorean identities as we see over here, if we try to match everything up, hopefully you can see here the one we're going to be using is this one over here. The 1 plus hyperbolic sine squared equals hyperbolic cosine squared. So we're going to be using 1 plus hyperbolic sine squared being equivalent to hyperbolic cosine squared. So if we think about the substitution we're going to be making, if we match everything up over here, you can see our substitution, we're going to have hyperbolic sine of u equaling f of x over a. Now let's suppose as well our integral this time has something involving f of x squared minus a squared square rooted, and because we're square rooting, for our substitution, when we come to think about our Pythagorean identities, we're going to have something involving sines, cosines or hyperbolic sines and hyperbolic cosines, and the one which matches up quite nicely is this one over here. So we're going to be using hyperbolic cosine squared minus 1 being equivalent to hyperbolic sine squared. So if we think about the substitution which we need to make, our substitution, if we match everything up, we're going to have hyperbolic cosine of u equaling f of x over a. Let's suppose now our integral involves something of the form a squared plus f of x squared. Now, if we think about the Pythagorean identities, first of all, you'll notice we're not square rooting, so we have to consider identities which involve tan, cot, or hyperbolic tan and hyperbolic cot. Well, if we try to match everything up, hopefully here you can see we're going to be using this one here, and we're also going to be using this one here. So one option we can use is 1 plus hyperbolic tan squared being equivalent to, 1 plus tan squared equaling sec squared. So if we think about the substitution which we need to make, we're going to have something of the form tan u equals f of x over a. And the other option we've got is this one over here, 1 plus cot squared equaling cosec squared x. So if we think about the substitution we should be making, we've got cot u equaling f of x over a. Example number 28. By using an appropriate substitution, we have to find the integral of 1 over the square root of x squared minus a squared with respect to x, where x is greater than a. So the way we will approach this question is to think about the trig identities cos squared a plus sine squared a being equivalent to 1, and if we rearrange what we have over here, you can see that cos squared a is equivalent to 1 minus sine squared a, and what we can also see is sine squared a is equivalent to 1 minus cos squared a. Well, none of these match up nicely, so what we have to do instead is think about the corresponding hyperbolic identities. Of course, we've got hyperbolic cosine squared minus hyperbolic sine squared, and that's because of Osborne's rule, is equivalent to 1. And if we rearrange from here, hopefully here you can see hyperbolic cos squared, that's equivalent to hyperbolic sine squared plus 1, and what we can also see is hyperbolic sine squared, that's equivalent to hyperbolic cos squared minus 1. And you can see over here this particular identity matches nicely with what's under the square root. So when we come to think about the substitution we're going to be making, if we notice what we have over here, hopefully here you can see for the substitution we're going to have hyperbolic cos u being equal to f of x, which is what x is, over a. So if we work out what what we can do over here first of all is rearrange for x. So x is equal to a lots of hyperbolic cosine of u, and we can also rearrange for u. You can see u is equal to the inverse hyperbolic cosine of x over a. So if we work out what dx over du is, dx over du, that's equal to a times by hyperbolic sine of u, and therefore dx is equal to a times by hyperbolic sine of u du. So what we will now do is replace everything as necessary. So if we do that, we've got the integral of 1 over x squared minus a squared square rooted dx. This is equal to the integral of, well, x squared, that's going to be a squared hyperbolic cos squared of u. So we've got 1 over a squared hyperbolic cos squared of u minus this a squared square rooted, and we multiply by dx, which we just said is a times by hyperbolic sine of u du. So if we factorize out the a squared on the bottom, we've got a squared lots of hyperbolic cos squared u minus 1 square rooted. On the top we've got a times by hyperbolic sine of u du. So if we simplify this result, we've got a over square root of a squared, which is simply 1. And then this, hopefully here you can see, is what hyperbolic sine squared is. So here we've got the integral of hyperbolic sine u du over hyperbolic sine squared u square rooted. So this and this cancel out. We're left with the integral of 1 times by du, which is u plus c. And we already know what u is. That's this result over here. So therefore, this is equal to the inverse hyperbolic cosine of x over a plus c. So that's how we go about these questions. When we find an appropriate substitution, we think about the trig identities and the corresponding hyperbolic identities, and we try to match up with whatever is in this form over here. And we essentially treat the a to be 1. And that helps match everything up nicely. And from there, as we saw previously in this video, we can match up and find out the substitution which we need to make. So like I've said, these formula are in the formula book, but just to reiterate, we've got the integral of 1 over square root of a squared plus x squared with respect to x. That's equal to the inverse hyperbolic sine of x over a plus c. And if we've got the integral of 1 over square root of x squared minus a squared with respect to x, that's equal to inverse hyperbolic cosine of x over a plus c, where x is greater than a. And you have to be able to prove this result. And just to convince you, in the formula book, hopefully here you can see those formula over here. So you don't need to memorize those. Okay, so we've got this one over here and also this one over here. Example number 29, we have to show that the integral of 1 over square root x squared minus 16 with respect to x in between 5 and 8 is equal to the natural log of 2 plus root 3 over 2. So to do this, obviously we can use the ideas which we saw over here, and of course you'll notice we need to use this result because this integral is in this form here. Now if a squared is equal to 16, a will equal 4. So we've got the integral from 5 to 8 of 1 over square root of x squared minus 4 squared. Now 4 squared is 16 with respect to x, and hopefully here you can see a is equal to 4. So working this out, we need to evaluate the inverse hyperbolic cosine of x over 4 in between 5 and 8. So if we work all of this out, you can see here we've got the inverse hyperbolic cosine of 8 over 4, which is 2, minus the inverse hyperbolic cosine of 5 over 4. So to do this, what we can do is look in the formula book under the hyperbolic section, and you'll notice for inverse hyperbolic cosine we've got this result here expressed in natural logarithm form. So if we use that idea, you can see here we've got the natural log of 2 plus 2 squared minus 1 square rooted, and then we subtract off natural log of 5 over 4 plus 5 over 4 squared minus 1 square rooted. So if we work all of this out, you can see here we've got the natural log of 2 plus root 3. And if we work out the result which we have over here, we've got the natural log of 2. So tidying all this up by combining the logs using the subtraction rule of logs, we've got the natural log of 2 plus root 3 over 2. Example number 30, we have to show that the integral of square root of 1 plus x squared with respect to x is equal to 1/2 times by the inverse hyperbolic sine of x plus 1/2 lots of x plus square root of 1 plus x squared plus c. So the way we start these questions is to first of all recognize that we need to use some sort of a substitution. Now here we've got a 1 plus x squared being square rooted, and because we've got a square root, we begin with these sorts of problems by thinking about the regular trig identity cos squared a plus sine squared a being equivalent to 1. And if we rearrange over here, you can see cos squared a is equivalent to 1 minus sine squared a, and what we can also see is that sine squared a is equivalent to 1 minus cos squared a. Now nothing matches up with what we have over here, because here we've got a plus, but here you can see we've got a minus. So we need to move on to the hyperbolic identities. You can see here, if we use the hyperbolic identities, we've got hyperbolic cos squared minus hyperbolic sine squared being equivalent to 1, and that's because of Osborne's rule. We replace the sine squared with minus hyperbolic sine squared. And if we rearrange for hyperbolic cos squared, hopefully here you can see we have 1 plus hyperbolic sine squared. And if we also rearrange for hyperbolic sine squared, hopefully here you can see that's the same as hyperbolic cos squared minus 1. So the one which matches up nicely is the result which we have over here. We've got the 1 over here, and we've got f of x squared matching up with the hyperbolic sine squared. So when we come to think about the substitution which we need to make, we've got hyperbolic sine of u equaling x over a, and a here is equal to 1. And if we rearrange for u, just in case we need it later on, that's equal to the inverse hyperbolic sine of x. And if we work out what dx over du is, that's equal to hyperbolic cosine of u, and if we rearrange for dx, that's hyperbolic cosine u du. So we can replace everything as necessary. We've got the integral of 1 plus x squared square rooted with respect to x. This is equal to the integral of 1 plus hyperbolic sine squared of u square rooted times by hyperbolic cos of u du. So this over here is what hyperbolic cos is. So we've got the integral of hyperbolic cos of u squared square rooted times by hyperbolic cos of u du. So here, hopefully you can see we've got the integral of hyperbolic cos squared of u du. Now the way we will approach this is to think about the identity involving trig, that is cos 2a is equivalent to 2 cos squared a minus 1. So the corresponding identity in terms of hyperbolics, that's equal to hyperbolic cos of 2a being equivalent to 2 times by hyperbolic cos squared of a minus 1. And if we rearrange, we've got hyperbolic cos squared of a being equivalent to 1 minus hyperbolic cos of 2a over 2. So we're going to use this result to replace this. So if we do that, well, if I also take the 1/2 outside, we've got 1/2 lots of the integral of 1 plus hyperbolic cos of 2u du. So if we integrate all this, hopefully here you can see we've got 1/2 lots of u plus 1/2 sine of hyperbolic sine of 2u plus c. Now the problem is over here. Well, if we replace the u with this result over here, we end up with this bit over here, and of course multiplying by the half we still get this over here. But the problem is I can't just replace this in terms of x, because you can see here x is equal to hyperbolic sine of u, but here I've got a hyperbolic sine of 2u. So the way we approach this is to think about the identity sine of 2a being equivalent to 2 sine a times by cos a, and then what we will do is find the corresponding hyperbolic identity. So hyperbolic sine of 2a, that's equivalent to 2 lots of hyperbolic sine of a times by hyperbolic cos of a. So if we replace as necessary, hopefully here you can see 1/2 lots of hyperbolic sine of 2u, that's going to equal hyperbolic sine of u times by hyperbolic cos of u, and that's because we're dividing by 2 over here. So what we'll end up with then is 1/2 u plus 1/2 times by hyperbolic sine of u times by hyperbolic cos of u. And the problem is over here, if I replace the hyperbolic sine of u with x, I get this x over here, and I've still got the 1/2, but the problem is I've got a hyperbolic cos u over here. But the way we can overcome that is to use the identities which we met over here. So we can rewrite this as 1/2 u plus 1/2 times by hyperbolic sine of u times by 1 plus hyperbolic sine squared of u square rooted. And don't forget we've got the plus c. So now everything is in terms of hyperbolic sine u over here. And if we use these two definitions to help us, you can see here we end up with 1/2 times by the inverse hyperbolic sine of x plus 1/2 x times by 1 plus x squared square rooted plus c, which is our final answer. Example number 31. By using a hyperbolic substitution, we have to evaluate the integral of x cubed over the square root of x squared plus 9 with respect to x in between 0 and 6. So if we're using a hyperbolic substitution, first of all you'll notice we're square rooting. So the hyperbolic will involve hyperbolic sine or hyperbolic cosine. So let's just begin by writing out the typical hyperbolic identity. Cos squared minus sine squared being equivalent to 1. And if we rearrange the results here, we've got cos squared being equivalent to sine squared plus 1, and we've got sine squared being equivalent to cos squared minus 1. Now, over here you can see this result almost matches this result. So you can see here a will equal 3 because a squared is equal to 9. So in terms of our substitution, if we compare with what we have here with what we have here, hopefully here you can see for our substitution we're going to have hyperbolic sine u equals f of x, which is x, over a, which is 3, the square root of 9. So from this we can rearrange for u. So if we rearrange for u, u is equal to the inverse hyperbolic sine of x over 3, and if we rearrange for x, x is equal to 3 times by hyperbolic sine of u. So now if we find out what dx over du is, that's equal to 3 times by hyperbolic cosine of u. So therefore dx is equal to 3 times by hyperbolic cosine of u du. And you'll notice our limits are in terms of x, so we need to change our limits so that they're in terms of u. So when x is equal to 0, we've got 3 times by hyperbolic sine of u equaling 0. Hyperbolic sine of u is equal to 0. U is therefore equal to 0. And if we have x equaling 6 for our upper limit, we've got 3 times by hyperbolic sine of u equaling 6. Hyperbolic sine of u is equal to 2, so therefore u is equal to the inverse hyperbolic sine of 2. Okay? So what we can now do is replace everything as necessary in terms of u. So therefore we've got the integral from 0 to 6 of x cubed over square root of x squared plus 9 dx. This is equal to integral of from 0 to inverse hyperbolic sine of 2 of x cubed, so that will be 27 times by hyperbolic sine of u cubed over x squared plus 9. So here we have x squared, so that will be 9 times by hyperbolic sine of u squared, and then don't forget we've got this plus 9 and we're square rooting over here, and then we've got dx, which we said is 3 times by hyperbolic cos of u du. So now we need to tidy all of this up. So we've got our limits as shown over here, and on the top we've got this 27 times by hyperbolic sine u cubed, and on the bottom, if we take out a 9, we've got 9 lots of hyperbolic sine of u squared plus 1, and then this is square rooted, and then we multiply by 3 times by hyperbolic cos u du. So square root 9, that's 3, and that cancels with this 3, and what we can also do is take out the 27 outside the integral. So we've got 27 lots of the integral from 0 to the inverse hyperbolic sine of 2, of, well, here we get hyperbolic sine of u cubed, and here this result is equal to, if we take a look over here, of hyperbolic cos u squared. So on the bottom we get hyperbolic cos of u squared square rooted times by hyperbolic cos u du. This and this cancel out, so what we're left with then is 27 times by the integral from 0 to the inverse hyperbolic sine of 2 times by hyperbolic sine of u cubed du. So now, as we saw in a previous example, we can tidy this up. So we've got 27 lots of the integral from 0 to the inverse hyperbolic sine of 2 of sine cubed, which I'm going to rewrite as hyperbolic sine squared times by hyperbolic sine. Now this we can replace. So we've got 27 lots of the integral from the inverse hyperbolic sine of 2 times by hyperbolic sine of u squared minus 1, which is what hyperbolic sine squared of u is, times by hyperbolic sine of u du. So if we expand out, we've got 27 lots of the integral from 0 to the inverse hyperbolic sine of 2. Now here we've got cos, hyperbolic cos u all squared, and I'm purposely writing it like this, times by hyperbolic sine u, and then we subtract off hyperbolic sine u. Then we've got the du. So now here we can use the reverse chain rule because the derivative of what's in the bracket is outside of the bracket. So we've got 27 lots of the integral from 0 to the inverse hyperbolic sine of 2 of this result. So we've got this, and therefore if we evaluate this, we've got 27 lots of, now here we add 1 to the power, so we've got hyperbolic cos of u cubed, and then we still have this hyperbolic sine u. We divide by the new power, and then we divide by the differential of the bracket, which is hyperbolic sine u, and then differentiating this we have hyperbolic cos u. Okay. So we're going to be evaluating this from 0 to the inverse hyperbolic sine of 2. So if we tidy all of this up, we've got 27 lots of 1/3 times by hyperbolic cosine of u cubed minus hyperbolic cosine of u in between 0 and the inverse hyperbolic sine of 2. Now to evaluate this, well, you'll notice over here, if we want our answer in exact form, if we substitute in over here, we're going to get something involving decimals. Even if I convert this to natural logarithm form, I'm still going to get something which looks quite horrible. But the way we can overcome this, if we think to what we said over here, we know already from here hyperbolic sine of u is equal to 2. So with this we can find out what hyperbolic cosine of u is. So if we do that, we have to use the result over here. So what this implies is that hyperbolic cosine of u is equal to 1 plus hyperbolic sine of u squared square rooted, which is equal to 1 plus, well, here we've got 2 squared square rooted, which is equal to root 5. So why is this important? Because now what we can do is substitute in everything as necessary. So if we use that, we've got 27 lots of, well, for our upper limit, we're going to have 1/3 times by root 5 cubed minus root 5. And then for our lower limit, we're going to have 1/3 times by 1, because hyperbolic cos of 0 is equal to 1, minus 1. So if we tidy all of this up, we have 27 lots of 5 root 5 over 3 minus root 5 minus 27 lots of 1/3 minus 1. So if we tidy all of this up, we end up with 18 root 5 plus 18 as our final answer. Example number 32, we have to find the integral of 1 over the square root of 12x plus 2x squared with respect to x. And the way we approach these questions, if we take a look at the denominator, we want to complete the square of what's under the square root. And that will make it easy, because we can then compare with what we'll end up with any of these integrals here. So if we do that, we begin with the 2x squared plus 12x, and what we can do is take out a2 as a common factor, so we've got 2 lots of x squared plus 6x, and then we can complete the square of what's in this bracket, so we've got 2 lots of x plus 3 all squared minus 9. So with that, we can rewrite this integral over here. We've got the integral of 1 over 12x plus 2x squared square rooted dx. So this is equal to 1 over 2 lots of x plus 3 all squared minus 9 square rooted dx. And what we can now do is take out the 1 over root 2. So we've got 1 over root 2 lots of the integral of 1 over x plus 3 all squared minus 9 square rooted dx. And what you can hopefully see over here, this is very much similar to this result over here, but instead of us having an x, this time we've got an x plus 3. So the way we can approach this is to make a substitution. We can let u, write it down in a different colour, we can let u equal x plus 3, and therefore du over dx is equal to 1, and therefore dx is equal to du. So what we'll end up with over here, if we change everything in terms of u, we've got 1 over root 2 times by the integral of 1 over u squared minus 9, and the 9 I'm going to write as 3 squared, and then we're square rooting this result and we're integrating with respect to u. So now hopefully here you can see, if we integrate this using the knowledge from what we have over here, instead of us having an x, of course we've got a u. What we'll end up with is 1 over root 2 times by the inverse hyperbolic cosine of u over 3 plus c, And we already know what u is, that's x plus 3. So what we'll end up with over here is 1 over root 2 times by the inverse hyperbolic cosine of x plus 3 over 3 plus c as our final answer. Example number 33, we have to use the substitution x equals 1/2 lots of 3 plus 4 hyperbolic cos u to find the integral of 1 over square root of 4x squared minus 12x minus 7 with respect to x. So if we expand this 1/2 into the bracket, you can see here x is equal to 3 over 2 plus 2 times by hyperbolic cos u. So now we can find out what dx over du is. Dx over du, that's equal to 2 times by hyperbolic sine of u. So therefore dx is equal to 2 times by hyperbolic sine of u du. So if we think about what we have over here, the 4x squared minus 12x minus 7, we want all of this to be in terms of u. And we already know what x is in terms of u, so if we replace as necessary, we've got 4 lots of 1/2 lots of 3 plus 4 times by hyperbolic cosine of u squared minus 6 lots of 3 plus 4 times by hyperbolic cosine of u minus 7. So if we tidy this up, you can see here we end up with 9 plus 24 hyperbolic cos u plus 16 hyperbolic cos u squared minus 18 minus 24 hyperbolic cos u minus 7. And if we tidy things up, we end up with 16 times by hyperbolic cos squared u minus 16. And we can take out the 16 as a common factor, so we've got 16 lots of hyperbolic cos squared u minus 1. So here you can see we've got 16 times by hyperbolic sine squared u. So we just need to use the identities where we can. So we can replace everything as necessary. So the integral of 1 over 4x squared minus 12x minus 7 square rooted times by dx, this is equal to the integral of 1 over 16 times by hyperbolic sine squared of u square rooted times by dx, which is 2 times by hyperbolic sine of u du. And if we tidy all this up, you can see here we've got the integral of 1 over 4 times by hyperbolic sine of u times by 2 times by hyperbolic sine of u du. So what we'll end up with is the integral of 1/2 with respect to u, which is 1/2 u plus c. Okay, so we know already what x is, so here we can rearrange for u. So if x is equal to this, we can rearrange from here to say that 2x is equal to, if we use this result, 3 plus 4 times by cos u. So therefore cos u is equal to 2x minus 3 over 4. So therefore u is equal to the inverse hyperbolic cosine of 2x minus 3 over 4. So we can use that result over here. And if we do that, we end up with 1/2 times by the inverse hyperbolic cosine of 2x minus 3 over 4 plus c. This is our final answer.